Hello, everyone. My name is Ivan. I'm a software engineer at Pure Storage. I know it's 5 p.m. and I'm probably standing between you and something fun to do in San Francisco, so let's hope to make this one fun. I'm going to be talking to you today about efficiently triaging CI/CD pipelines with Apache Spark. And we use a combination of streaming and batching. We stream over 80 billion events a day, and we batch 40 terabytes an hour throughout the day at different times. So, because I know I need to capture your attention early on because I don't have it for very long, in numbers, what we do in our log analytics pipeline, we process about between 900,000 and 1 million events per second. Our SLA for the actions that are taken based on some of these events is 5 seconds. And on the batching side, we reprocess about 0.5 to 1 petabyte of data every single day. So let's get started. What is continuous integration and continuous deployment? Maybe some of you are not familiar, so let me walk you through quickly what that process and that workflow is. In software engineering, it's how we essentially deploy tests quickly, and how do you integrate automated testing to make that happen. As a software developer, everyone's familiar with repositories, so normal developer process, you check out the code from your repository into your generally local machine. Get the source code, make your changes, and then you build it, right? You hope to have built something. Most of the time, we don't build the right thing. So you run your unit tests, generally in your local machine. The next step from unit tests is functional level tests. That's where you check that the functionality you think you built is actually what you built. And of course, you have to check that the functionality that other people have built, you did not break with your new functionality. That's functional level testing. Stress testing is now more about testing at scale. You can think of performance testing or longevity testing. In our world, we build storage products, so we think about season data, longevity, how long has the data stayed in our system, how many times it's been touched. And if it passes all these different checks, now you're good to deploy this code to whether it's your customers, to your web application, or whatever it is. This talk is mostly going to be focused on the functional level testing and the stress testing. Those is the most scalable applications that we have, and they generate just a lot of messy log data. So why do we care, right? CI/CD works really well for us. We invested in it very, very early on when we were just a handful of engineers. We built a product called a flashlight, which is that little white box that has late-looking things that are vertical. When we started, we had less than 5 of these prototypes at a time. And it's a storage platform, so you need to be able to have machines that are driving load, that are doing the reading and the writing from the storage platform to be able to test it. There were so few of us that we had a single branch of development, right? We were a startup, small group of people. And it worked really well for us. We had about we would run hundreds of tests per day. Less than 5 failures because most of the testing is done in your own local environment, so you catch most of the bugs that way. And the system was so primitive that it would just email the last developer that made a code change every time there was a failure. That developer was in charge of triaging that problem, figuring out why it failed. And if you didn't break it, probably you did, but if you didn't break it, figure out who broke it and then assign it to the right person, right? We didn't even have a ticketing system. We just would email one another, or maybe sometimes just walk over and tap you on your shoulder. So this worked great, and it was very, very valuable. We were able to really have predictability in the software development process. You fast forward to today. Lucky for us, we've done well as a company. We have a lot of demand for our products. There's a lot of features that we need to build for our storage products. So we have over 100 software engineers just for this one product, the FlashBlade product. Now, it turns out these products are expensive to build, and we cannot just go buy thousands and thousands of them. So what we had to do is we had to go build simulations of our product. So a lot of our functional level testing that we do, we can do on simulated software, on simulated hardware. And these 1,500 VMs that you see right here, that's what they're doing. They're simulating our FlashBlade products, so we can do all of our functional level testing there. Then we have about 250 of our FlashBlade products. That's where we're doing the stress testing, the longevity testing, season testing, performance testing. We have over 700 clients. They're just bare metal machines. Their job is to run this test. They're doing our customer essential operation. They're like reading and writing from storage and doing a lot of weird metadata operations and things like that to prove that the storage works. We have a lot of releases now, so we have to maintain release branches, and we have a lot of teams that are working in parallel to build different features. So we have over 20 different features branches, and between feature branches and release branches. And we have multiple Jenkins instances because Jenkins doesn't scale out, it just scales up. So we have multiple Jenkins instances, and we have to triage them all. On any given day today, we now run over 70,000 tests. Now, that number may not sound very, very big to you, but on a software development shop, it is not abnormal to have like a 1% failure rate. That's actually very conservative. So when you think about that, that's 700 failures every day. Now, why does a failure take so long? It takes 15 minutes today to triage, for a human being to triage that failure. It takes so long because each one of these tests is essentially trying out a bunch of different components. You're testing the storage platform and the code in the storage platform, but to test the storage platform, you need to have switches in the middle, you need to have test code, you need to have the initiators that are driving the actual read and write workload. So the job of the engineer who's in charge of triage when you have a failure is to go look at the testing, figure out what the output of the testing is, and then try to correlate that little by little throughout the whole step, all the way into our product, the FlashBlade. Our product itself is a distributed system. It has many, many nodes. Each of the nodes look exactly the same, and they have the same different pieces of software stack. So now you have to correlate whatever failure you think from the FlashBlade product into each of the different products, into each of the different subcomponents. Each of the components has at least 10 different pieces of software that are running, and each one of them is generating logs. And now you need to follow the same path. So a triage engineer has to correlate time data from all the way up in the level, the failure of the test, down to sometimes even the hardware level, because we build a hardware product. So very conservative estimate of 15 minutes to triage and understand who's the right engineer to assign this to. Not even to fix this problem, just to assign it to the right person to take a look at it. What that means for us is that we would need 20 triage engineers. That's 20% of our workforce. We cannot afford that, right? We still want to feel like a startup. We want to move fast, so we cannot do that. And the first thing that we realized was that even though we have 700 failures every day, we don't actually have 700 bugs. I promise we ship good stuff. So we really have about 30 to 40 actual root causes underneath. And these problems that are introduced, some of them are long-lived, and we know they're there, and they're like not affecting real workloads, and they're just testing problems. And some of them are introduced by our software engineers that are developing every day. And some of these root causes may manifest themselves in different symptoms, in different tests, in different branches. So what we found was that our triage engineers were repeating the same process over and over again, wasting time triaging the same root causes. So we wanted to automate this, right? And to make things worse for us, everything on the left is double in the next 12 months. We have high growth plans as a product and as a company, so we want to double all of our engineers. So how do you automate this, right? The first thing you got to think about is you have to imitate what the humans are doing. The humans are looking through logs and correlating through logs. So the first thing that we wanted to do is create a system so that our triage engineers could encode what they're finding, could encode the patterns of the logs and the sources. So you can think of a triage engineer saying, if a test said that it failed to read and the switch was OK, and the fabric module, the switch inside the FlashBlade is OK, and one of the blades happens to perform operation X, and the other one perform operation Y, and operation Z did not happen in the middle, then is this problem. You know, that kind of logic that you want to encode from logs will map into a unique root cause. So we wanted to provide a system for that. So what else do we want to provide? We're going to be processing logs, we said. Let's design a log analysis system that can give us, give us more than just this. So obviously we talked about automation of the triaging of failures as much as we can. We also wanted to extract performance metrics. Like any other product, we test our product really, really heavily. We push it to the brink, right? We push it to the maximum. We try to, obviously, as we release new versions of the product, we don't want to release something slower than it was before. It's the same hardware. It should perform as well. But additionally, we're also injecting a lot of failures. As I said, this is a distributed scale-out system, so any one of the components can fail, and we have to be a resilient product for that. So we've built software that allows us to fake these failures. So, but during some of these failure scenarios, we're not actually measuring the performance, so why should we not be doing that, right? Obviously, we want to save our logs for future use. Everyone's paranoid about having a day zero bug that you might have to go back in time all the way to the beginning and find and maybe look for some patterns, or maybe there's a customer that has an issue, and we want to figure out, did we see this pattern in the logs before at some point in the past? We talked about how we're growing 2x, so scalability was key in our design. And lastly was obviously real-time results. When you're thinking of continuous integration, how quickly you can take actions based on what's happening in your environment matter, because that can significantly reduce the amount of noise that the failure tests create. Noise in a continuous integration system is probably your worst enemy, because at the end of the day, the goal of a continuous integration system is when you make a change, you want to know that a new failure that happens is because of your change and not because of something that was already in the environment. So reducing noise was the most important thing. So how quickly you can take action matters. So let's take a step back. Let's take a look at log analysis, right? This is your logs, this orange triangle here. You have data that is all the way on the left, that is really, really high volume, that more likely than not, it is log spam. Some developer wrote that they just, oh, this would be good to have, but they're never really going to use it. And all the way on the right, you have these patterns and these errors, say, as an example, that you really, really want to take action on. So as you're building a system and your log analysis is evolving, you want to be able to extract the value out of the stuff on the right? The log data that has the most value. So we obviously talked about how we have to save everything. So the first step is you need to be able to design for something where you can just take alert and actions on really the few things that you know are important. You might need to apply some logic to those, as I mentioned earlier, but there's really not that many of logs, especially when you're starting, right? You don't really know all the questions and all the weird patterns that you want to capture. Obviously, as I mentioned, performance metrics. We want to get the data out. We want to visualize it. We want to make pretty graphs so that people don't have to create greps and awk scripts, because that's the world that we lived in. So being able to ETL some of your data, put it into a structure that can be queried and can be visualized was important. And lastly was, sometimes you just want to aggregate data. You just want to see, this log line, maybe it doesn't have any data itself, but how often it happens is important, right? Or maybe you want to create a searchability, but you don't necessarily want to go search everything, right? Because you might have a lot of data. So really trying to figure out what is important to you and when. And if you build one of these log analysis systems that can scale well and you can, over time add more and more value, you will hopefully end up in a world that looks like this, where you end up ETLing more and more data because you find that there's more and more data that you're using, whether it's because you're adding new features to your product and engineers decide that, oh, I can actually add data in my logs and I don't have to figure out a database or some way to inject it somewhere else. Or searchability becomes more important based on warnings, errors, different levels of logs that you might have. So with these concepts in mind, how do we think about a log analysis pipeline now in terms of processes and the design? First, you obviously have your log sources. The first step you got to do is you got to centralize the data into a single spot. And then you got to augment it. The augmentation step at this point is so that it allows you for easier searchability later on. The augmentation can be something as simple as, where is this data coming from? Right? For each of the logs, as I mentioned, we have a lot of different products, a lot of different versions. We're injecting different log sources. So just tagging the data with metadata will make it much easier to search later on based on the use that we might have of the logs. And you obviously need to store that for long term. From this point, you have to think about what are your uses all the way on the right. We talked about 3 different use cases in our world, which is the logic that we want to apply. We want to transform into a time series database in this case because logs are just time series events. And we want to aggregate it and maybe visualize it as well. So when you think about the consumers of this data, they need to get efficient access to the data. And the only way to do that is by putting, obviously, an index in the middle. You have to create an index for this data. Now, the first thing that you realize when you think of this system is, man, I show you this big triangle in the middle, but really the value that I'm extracting is all the way on the right. And you find out that indexing is a really, really expensive operation compute-wise, right? It's a database. You're building a database from all of your data, but you don't necessarily want to do that because you're not going to use all of your data on the right-hand side. So if you don't want to use all the data on your right-hand side, what is your only option? You have to filter, right? Everything on the right-hand side is programmatic today. So you know what data you need today. So therefore, as your data is being streamed in, you're able to filter the data and then only index the filtered data, the data that you're going to be using on the right-hand side. Now, if you're streaming, you have to add a streaming buffer in the middle, mostly because data is generated in bursts, and you want to sort of normalize that so that the compute that you use for your filter is a lot smaller and consistent. Now, filtering, in terms of compute compared to indexing, is between 1 and 2 orders of magnitude cheaper. So this really allows you to, I can apply a filter to all my data all the time, and I still don't have to pay lots of money to do that, right? So now I live in a world where I've indexed only what I need. And your next question is obviously going to be, well, I don't know what I'm going to need tomorrow, right? In the streaming world, I can, at any time, if you build the system right, you can add more things to filter on, and that will get you stuff going forward, all your new filter patterns and index patterns. But if you want to go back in time, which a lot of times is important, the only option that you have is, well, you have to find a way to refilter from your raw data. And when this happens, and when you come up with this realization that that's the only way around, this puts pressure on your storage, right? Because in the past, you just needed a storage that was able to keep up asynchronously with the ingest of data that was being streamed. But now you need a storage system that not only can it save the data, but can also deliver the data at high throughput amount so that this refiltering step and indexing step can be done in an efficient way, right? If the delivery of the data from the store to the refilter and indexing is so slow, it can become prohibitively expensive time-wise, right? You might not have enough time. And I'm going to talk to you about some of the numbers that we have later on so you can have an idea of what are some of the scale that we're talking about here. But before we do that, let's talk through the actual technologies that we use to fill each of these boxes here. In our case, most of the data on the left is actually created by syslog. And because of that, the actual transitive, easy choice right here was remote syslog, our syslog. They're just remote syslog servers. They're just sitting there waiting for data to arrive over the network. And our syslog, you can teach it to apply whatever metadata and tags and build something like JSON or whatever other format you want from your data. So we use our syslog here. And from our syslog, that data is being fed in two places. One, to the streaming buffer, and second, to the store. We are a storage company, so obviously we use our own storage, right? We use this FlashWave product, which is a scale-out file system and object store. We use NFS. Everyone knows NFS, and everyone believes NFS is really slow. Let's have a conversation after. But on the streaming buffer, we use Kafka, and that's obviously the most common choice today. But Kafka allows us to buffer. It allows us that if the next filtering step goes down for whatever reason, because at the end of the day, it's code, when it comes back up, you can pick up wherever you left off. From the filter step on the streaming side of the house and on the batching side of the house, we use Spark. The fact that Spark has both a streaming interface as well as a batch interface allows us to reuse the same code. It's exactly the same code, and we can just run it in different modes, right? It's just whatever functions you're using to call Spark. On the index side, and this is where it gets really interesting for us, we use the file system. This is step 0 for most people. Right? For most people, you say, well, I want to know where this data is going to, right? I'm trying to put the data into buckets. So the first step is you say, well, I'm going to add a prefix to the data. I'm going to say, data X underscore whatever, or data Y. And then when you're searching, you can search the file system, and you find it. Now, when you don't have very much data, that generally works. Because we have built a scalable storage system that actually can handle billions and billions of files, and can handle small and large files, this actual index on the file system scales really well for us over time. This little storage box can deliver 1.5 million I/O operations per second, which means we can actually search through the file system really well. We actually use the directory structure of the file system to index the data. So we have an index that looks like year, month, day, hour, minute, key, and subcomponents. And then inside the subcomponent directories, we have the files that actually, in flat files, they're storing JSON content, and they're storing the actual index data. So from the consumer side on the right-hand side of this index, all of them are just querying the metadata of the file system, extracting the data that it wants, and processing it. So as you can see from the right-hand side, all of these are just operations that you're performing on data. So you can think of them as functional programming, like Lambda style. So for us, they all look exactly the same. They're just Python code that are reading from a place, that are watching whether events are coming in, events that have been filtered, and pulling from those. On the right-hand side, which is the final consumers of all of this data, and after the transformations or aggregations, so the logic has been applied, we have InfluxDB as our time series database, Grafana as our visualization, and we use more Python as our intermediary to alert on all the events that may be happening. Python has a lot of nice plugins to do essentially everything, whether you do PagerDuty, Jira, Jenkins. We alert to email. We alert to a bunch of different systems based on different events that may be happening. So conceptually, this is what we've built. In terms of physically and numbers-wise, what we've built looks a little bit more like this, right? We start with the data sources that I mentioned to you earlier, all these numbers that are here. All these data sources are generating 9 terabytes of data every single day. That's a lot of data. And all of those are going to our syslog servers. Each of these little gray boxes in this image represents a VM or a machine. And the numbers inside of the little gray boxes are how many cores it has, just to give you an idea on how much compute we're using for this. So 6 rsyslog servers with 16 cores each. At this point, the rsyslog server is taking these 9 terabytes and augmenting them by putting metadata on this data from all the 70,000 tests that they're running. It's augmenting it with things like this is the SHA of the code that it's running. This is the Jenkins label that it's running, or the Jenkins branch that it's running on. These are the labels of the node, et cetera, or the test, et cetera. rsyslog is saving the data to the flash array, as I mentioned earlier, for future use. It's all going to the flash array. And it's also sending that data to Kafka. The augmented data is now bigger, obviously, right? It's now 27 terabytes. And those 27 terabytes are going, again, both to the flash array and to Kafka. Kafka is then the distributed messaging queue right here. And that's where Spark comes in. Spark was taking all of the filtering patterns that we need to find. And it's what's constantly monitoring and pulling from our database of patterns that we've provided. We provided a CL, essentially a UI for our developers through Jira, where they can ingest, input these patterns. And Spark, at each one of its micro batches, is pulling all these patterns and doing the filtering from here. From here, Spark is sending those 300 gigabytes down to the file system, as I mentioned, through the index. That's a little hard to display in an image, so I just have skipped it directly to the Python process. But yeah, so those 300 gigs are going down to the flash array as an index, as a storage platform, and the Python processes are pulling them directly from there. As you see, the input rate whenever I took this screenshot, which was early this morning, was about 920,000 messages per second. And those are the number of messages that are being filtered. You can do the math to figure out how many messages we're actually getting value out of, which are those 300 gigs. The average size of messages for us is between 350 and 500 bytes, depending on which software is creating. They're log events, right? Syslog events. And eventually, the value, right? This is really the value of the data and what people can actually take action on. The kind of things that we report on from this pipeline are things like, hey, this is a duplicate bug, or you have an infrastructure failure, you should shut off all these infrastructure that you have here, stop the test, and these kind of things. Or we have a performance regression, somebody should take a look at this code and analyze, go deeper. And as I mentioned earlier, you have to also be able to go back in time. So what happens when one of our triage engineers goes and adds a new signature that represents one of these failures? We now need to be able to go back in time. So what we do is we have another Spark cluster. And in our case, we now can control how far back we get to go. We happen to store the data for 2 years because, again, we're paranoid and we're going to always be able to go back in time. So, but for the test failures, we really only care about the last 3 days, right? If your bug happened more than that, whatever. It should already have been triaged manually. So we go back for the last 3 days, and that's 81 terabytes of data. We process it through only the new filters that have been added since the last time this was run, and we extract however many patterns. In this example, this is one of those runs, happen to extract 30 gigs into the index. If you add a different signature, you might end up extracting 300 or 500 or even a terabyte of data. Different amounts of, different signatures will require different amounts. And it obviously goes through the same Python reporting to hook into all of our other services. And to take this even a step farther, I mentioned if you build a good system, people are going to want to use it and are going to tell you all the more things they want to do with the logs. And people started coming to us with more uses for the logs, so we had to build more. Turns out that this performance data that we're getting is great to measure performance at the top level. But there's a lot more events in the logs, low-level events, all the way down to the flash, right? We don't use SSDs inside our products. We use raw flash chips. So our hardware team comes to us and says, I want to know how the flash is wearing out over time. And we happen to have data in the logs. Can you, ETL it and visualize it for us? And we may only need to do this at time of release or maybe only once. But for this example, we, let's take a look at a week of data and see, what's valuable, what's not. Let's explore the data. So we can do that. We can use the same Spark batch cluster that we have there. Obviously, people are not really adding these signatures at night, so we can just reuse it at night. We can pull the last 7 days worth of data, which is 189 terabytes. We pull out 50 gigs, same concept, apply the Python ETLs, and now push that over to an InfluxDB that will, now you can visualize very nicely that week Grafana. So one of the reasons that we can build this system and essentially scale the different parts at different times is the main reason why different subsystems can scale, right? if at any given time you need to index more because you have had more signatures, you need to be able to scale the part that is indexing, right? The part that is filtering is sort of fixed because data, yeah, sure, it grows as we install more flash plates, more VMs on the left-hand side, but the indexing part needs to scale, and the processing part afterward also needs to scale. So one of the key concepts for us was the most important thing to encode here was the disaggregation of compute and storage. Funnily enough, in the same inline as our last talk, right? The disaggregation of compute and storage for each of these subsystems allows us to scale them based on the requirements of a given day. Whether you need more throughput or whether you need a longer storage retention rate, you should not need to add compute and storage for both. You want to add compute when you need compute to handle throughput and compute-related operations, and more storage when you need the other. So a disaggregation of computer storage was key for us to be able to scale each of these subsystems. So to close, the takeaways for us as we build this is one of our key design principles was really build a system that indexes only what you need, right? And store the rest. As long as you store it in a storage layer that scales to like billions of files if you want to use the file system as your index. If you don't, you still need scalability in terms of throughput. IOPS may not be as important, but scalability matters. And the last one, to be able to control how much each of these subsystems grow, you need a disaggregation of computer storage for each of the subsystems. So thank you very much, and I'll take any questions if you have it.
All right.
How did rsyslog scale for you with so much data flowing through? And did you see any drops in the data?
That's a great question. rsyslog was the most flaky piece of software that we've ever worked with. So because we control the log sources, we can control the scalability of which rsyslog servers the data goes to. So essentially, the code that runs on all of the applications on the left can pull a service that we've created that will tell you how loaded each of the rsyslog servers, and you'll pick the least loaded one. Every time we bring in a new log source, we first bring it in via UDP method, because if the data is too much, if it's bursty or the rsyslog cannot keep up, it will not disrupt the other sources. It will just start dropping logs. But as we get a better understanding of the new log source that we brought in, we eventually switch it to TCP, and when we already understand what kind of load it's putting in. Yeah.
Had a question over here somewhere?
Hey, I have two questions for you. One on the indexing. So indexing is based on your use case, right?
Sorry, indexing is what?
The index you created, it's based on your use case only, right?
Yes.
Okay, the second question is which pipeline you use, any pipeline software you used for doing everything end to end?
So it's essentially whatever you want, right? So one thing that I didn't necessarily talk about is that actually in between the index, at the same time the data gets pushed into the index, we actually also push notifications in the middle through Kafka. So Python, we just have a bunch of Python consumers that are essentially listening on Kafka topics, and they can trigger different Python processes that are taking the action. But one of the good things about this system is that most engineers can write Python. And if we allow essentially, our goal, not yet, but we will allow to build your own ETL essentially, where you define the patterns and you come with your Python files and we'll install it all for you into our pipeline. Our pipeline is actually all containerized. Everything runs in containers. This makes it really, really easy to scale. And the fact that they're all totally stateless containers because it's all disaggregated compute and storage, scalability is super straightforward.
Any more questions? Oh, right here.
Yeah, I was curious, what do you use for resource scheduler for your pipeline? You said it's containerized, but is it like Mesos or something like that? And then also, why not use something like Apache Solr for indexing, or some other like Elasticsearch or
Yep.
something like that? Thanks.
So the first question, so for the orchestration and the resource management, we actually happen to use Nomad. That's because that's what we've been using forever inside our company. So no particularly good reason of Nomad versus other orchestration systems other than, I guess technical debt. For the indexing part, we did it because we could. That's really the only answer. We know exactly what the use cases of the data are. So we know exactly what keys and primary and secondary keys, and we don't really need more than that. So if you do need full searchability of the data, obviously you need a better indexing system, like a reverse index like Elasticsearch. But for our use case, it was completely unnecessary. The file system metadata is more than plenty for us.
All right, I think we are reaching our time for this session. If you have any further questions, please feel free to see the speaker outside afterwards. Let's have one more round of applause.